So in the previous class we learned uh, what do you mean by, or we have defined a magnetic circuit, and we also compared the two circuits in two energy domains. One energy form is electrical energy form, and the another energy form is our magnetic energy form, right? So, and uh, we also compared the various analogous quantities in an electric circuit and in a magnetic circuit. That means we have current, we have the cause, that is voltage or EMF, electromotive force, and the effect of that cause is our current, and we have opposition to the current. We are defining in electric circuit that as resistance. In the same manner, in the same sequence, we have analogous quantity of EMF, electromotive force. We have here magnetomotive force, MMF, and current, which is the effect of the EMF. We have analogous quantity in magnetic circuit. We have flux, and then we have the analogous quantity of resistance in coming to the magnetic circuit. We have opposition to the flux flow, that is reluctance, that is S. Okay, now we are now again consider our previous example of a magnetic circuit. We have considered a toroid. This is the toroid figure like this. This is our toroid, and this toroid, suppose it is having a perimeter length L, L meter, and it is wound by a winding of capital N number of turns, like this. And it is carrying a current I. Its N is equal to the number of turns. And yes, let us assume that this setup is carrying a current I, and its perimeter length is L meter. Okay, that's given. Now it is sure that this toroid, which is suppose assume that this is made up of some iron or a steel, then inside this a flux will be set up, right? Now we are going to define the uh, magnetomotive force, MMF. MMF, that is magnetomotive force. It is defined as the number, like this. Magnetomotive force is defined as the total current. It is the total current linked with the magnetic circuit, namely IN. That is the total current linked with the magnetic circuit. That means here I is flowing in, I will flow here and from here to here and here to here and then in this direction, right? And out of the toroid like this. So magnetomotive force is defined as the total current linked with the coil of capital N number of turns. So it is equal to Ni, and is known as mmf is also known as ampere turns. Ampere ampere turns ampere turns, and its unit is ampere turn ampere turns, AT. Okay, so mmf magnetomotive force is also called ampere turns, that is AT. Okay, mmf, and it is equal to Ni, and its unit is a a only, ampere. Actually it is ampere. Turns means it is a number, right? So it has no unit, so ampere, mmf unit is ampere. And if you and this mmf is independent of the uh, material, independent of this material, that is this independent of the material made by this toroid, that is toroid material, independent of the toroid material, whether it is iron, uh, steel, or any other magnetic material. Okay, nickel, copper, any other conductor or a magnetic material, your alnico or any other magnetic material. Okay, it does not depend upon that magnetic type of magnetic material. It depends only on the number of turns and current I. Okay, current I carried by this number of turns or binding. So that is what I mean by magnetomotive force mm. And again this now we are going to define another term that is known as yes, actually this toroid is of uniform cross-sectional area. That means if you consider a cross-sectional area A here, okay, A like this, and this will be if you consider a cross-sectional area here also, then this will also be A. Okay, at any point you consider a cross-sectional area, it will be equal. That is what I mean by uniform cross-sectional area. Even though in the picture it is not like that, but we are assuming that this uniform cross-sectional area, that's that toroid is having uniform cross-sectional area. And we are going to define another term known as the magnetic field intensity. Magnetic field intensity, and it is denoted by H, capital H. Okay, magnetic field intensity, and this magnetic field intensity is also known as magnetization. Magnetization is also known as magnetization. Okay, magnetization, and also it is or also known as it is also known as magnetizing force. Sorry, magnetizing force. Magnetizing force. Magnetizing magnetizing force, and it is also known as magnetic field strength. Magnetic field strength. Okay, so these are the various names given to this magnetic field intensity H, and H is defined as H is equal to, if you divide this mm of magnetomotive force by its length, then you will get H. That means it is defined as the magnetomotive force per unit length. It is defined as the magnetomotive force or ampere turns, AT, ampere turns per unit length of the toroid. That is N I divided by L. Because why? Because its mm, circular length of the toroid is considered as L meter. Okay, why? Because actually it is not exactly L, but we are taking an average. Why? Because here we will have an inner radius, and also we will be having an outer radius. But okay, so the length will be we will have two lengths, two perimeters, but we are taking an average value that is passing through the center. So that is we are taking it as L. So H is equal to Ni by L. That is what uh, magnetic field intensity is defined. Magnetic or magnetizing force or magnetic field strength, and its unit is ampere turns, AT per meter, or ATM inverse. Okay. So unit of of actually it is ampere, but uh, we are taking it as ampere turns AT as the unit. So it's so the unit of this magnetic field intensity will be ampere turns per meter, per meter. So okay, so H is measured in ampere turns per meter per unit length. Okay, so that is a magnetic field intensity H, and this magnetic field intensity H is independent of the, it is also independent of the medium. Okay, its value depends only on the number of turns capital N and the current I flowing in the coil. That means uh, if you want to if you want to the if you want to increase the magnetic field intensity or magnetizing force in inside this toroid, okay, inside this toroid, either you have to increase the number of turns, okay, or you have to increase the current magnitude, or both you can do, or you have to decrease this length. Okay, length of the toroid. So that is the magnetic field uh, intensity. Okay, now I'm going to define another term that is known as the magnetic flux density. Yes, magnetic flux we know. So here it is nothing but magnetic flux density. So density means it will be some per unit area or unit length or per unit volume, right? So like that. So magnetic flux means, sorry, magnetic flux density means it is the number of magnetic flux lines passing per unit area. That means if the magnetic flux is phi, phi is the magnetic flux uh, notation, then phi divided by the cross-sectional area A. That is what you mean by magnetic flux density B, right? B. Now we have the magnetic flux. The unit of the magnetic flux is nothing but Weber. Unit phi unit is Weber, and it is denoted by WB. And area unit is meter square. So magnetic flux density B is, unit of B is Weber per meter square, or that is also known as Tesla T. Tesla T. That means 1 Weber per meter square will be equal to 1 Tesla, 1 T. Okay. So that is the magnetic flux density. Now suppose we have this medium, that is we have in this figure, that is figure 1, the winding is placed on a toroid, and that toroid is made up of, we are assuming that it is made up of iron or steel or cast steel or some other magnetic material, right? Now suppose you imagine this toroid, okay, made up of iron or steel is replaced by vacuum or air, vacuum or air. Okay, that means you will not have this boundary lines, right? So if the core, so this is called as the core. So the core, if the core is made up of or is filled with a vacuum or air, then the ratio of uh, magnetizing force H, the ratio of magnetizing force S, okay, and the magnetic flux density B will be a constant. That means I repeat once again, if this core is replaced by a medium, vacuum or air, okay, vacuum or air, if you replace this core with this either of this medium, that is vacuum or air, then the ratio of magnetic flux density we have defined, and the ratio of this magnetic flux density to the magnetizing force H, or the magnetic field strength or magnetic field intensity, will be a constant, will be a constant. So the scientists found this observation. Okay, so they have conducted so many experiments and they found that this ratio is constant, and this constant ratio is defined as our next important term, that is magnetic permeability, okay, of free space or air, free space or air. Okay, then that is represented by mu 0. So B by H will be equal to mu 0, and this value is found to be 4 pi into 10 power minus 7. Okay, yes, Henry per meter. Okay, now if you want to find out the flux density, okay, flux density sorry flux density at a point inside this core, okay, inside this core I'm considering a point P, and if you want to find out the flux density at this point, then yes, given magnetizing force, then the relation you have to use is B at that point. B will be equal to mu 0 H, that much Tesla or Weber per meter square. Yes, any unit you can use. So that is our relation. Okay, now now we are going to extend our discussion on reluctance. Reluctance, yes. Okay, yes. Let us take up the uh, yes, the same toroid. Okay, in this manner. It's a toroid like this. And its mean length is uh, L meter, L1 meter, okay, L1 meter, and I have the cross sectional area of this toroid like this. Okay, this is A1, okay, A1, and the yes, magnetic permeability, okay, magnetic permeability of this core, which is made up of some iron or some magnetic material, okay. I'm denoting it as mu m, that is mu m equal to magnetic permeability of the medium, okay. Yes, so now uh, actually from material to material, this magnetic permeability will change, and that means this actually this magnetic permeability means uh, how easily uh, flux the flux will penetrate, will travel through that medium, okay. That that its measure is what is mean by magnetic permeability. That means magnetic permeability is high means uh, it easily conducts, or it easily allows the traveling of the magnetic flux lines, okay, like our iron. Now here I am, yes, I am, let us imagine that a current I is flowing in this way, okay, this way, okay. So what happens is a ni will set up, n number of turns is there, and current is flowing through that winding of n number of turns. So what will set up, a magnetomotive force mmf will be generated, will be set up in this here, okay. That means mmf, that's equal to nie is set up, and that magnetomotive force, which is the cause, okay. If there is a cause, then there will be an effect. So what is the effect? Effect is nothing but your flux like this, flux line. So like this, a large number of flux uh, flux lines are set up in the core, okay. Now I'm considering, so this flux lines, let it be phi, okay. Phi is the magnetic flux lines, okay. And let S1 be the reluctance offered by this medium to the flow of flux phi. So and now this is our case 1. Now I'm considering another case 2. The same, yes, the same toroid, but what happened is, yes, same number of turns, okay, and same current I is flowing, okay, same number of turns N, so that magnetomotive force MMF is same Ni ampere turns, and the flux setup is also okay. Anyway, flux. Now what happens is, now the flux. Wait for that flux. Yes. What will happen? The magnetomotive force, because of the magnetomotive force, a flux will be flown. Okay. Flux will be set up in like this, like this. So what you can observe from case 1 to case 2 is that what is happening, what in case 2 we have considered the toroid of cross sectional area A2, so that A2 is greater than A1. Okay, now, and the length, okay, length, suppose let the length be L meter, L1 meter, sorry, L2 meter, okay, L2 meter, such that this L1, that is which is the length of the previous, okay, L1 meter, and that L1 is equal to L2. Suppose you assume that length is same, but the area is somewhat increased. Okay, then what is happening here is more, okay, the flux lines, more number of flux lines are carried or confined by this toroid. Okay, that means the same flux, the same number of flux lines, now they can flow in a larger space. They can spread in a larger space, or they can easily flow around the toroid. That is what happened by increasing the area from A1 to A2. Okay, that means the ease with which the flux lines are flowing got increased, right? That means the opposition to the flow of flux lines got reduced. Okay, that is our observation. So our observation is opposition to the flow of flux to phi is reduced. So now I'm considering another case in which the same toroid, okay, toroid of same cross sectional area. I'm in this case I'm fixing this cross sectional area A1, sorry, A3, that is equal to A1. Okay, but the length of this toroid is L3, but L3 is greater than L1. That is, length got increased, but other things are same. That means current I is same, and the winding is having the same number of turns, so that in the same direction, so that the MMF is same, that is MMF is equal to Ni ampere turns. Now the flux setup. So the flux lines will be produced, and these flux lines are traveling, okay, in a larger distance compared to the previous case one. Okay, that is, the flux lines are in this case the flux lines are traveling only L1 meter length, but in this case the flux lines are traveling for a much greater length, that is L3. That means L3, because L3 is greater than L1, but the cross sectional area is, let us assume that, same. Then what happens is the opposition to the flow of flux is increased, because the chance to oppose the flux is got increased by increasing the length, because more length, more length, the flux of phi has to travel, in this case, more length. In this case the flux phi has to travel more length, that is L3 greater than, which is greater than L1. So what happens is the opposition, so our observation is opposition to the flow of phi got increased. This is our observation. So I'm concluding our observations. Okay, I'm concluding our observations. That means the opposition to the flow of flux lines, which we have defined as the reluctance, is directly proportional to the length, and it is inversely proportional to the cross-sectional area. That means if you increase the length, then the opposition also increases. That means reluctance offered by the material increases, and if you increase the cross-sectional area, then the opposition got decreased. Opposition means the reluctance S got decreased. So S, reluctance S, is directly proportional to L, and it is inversely proportional to A, and S is equal to a proportionality constant K into L by A, and this K, proportionality constant K, is 1 by mu M. That means S is equal to L divided by mu M, where mu M is equal to permeability of the medium, permeability of the medium with which, or through which through which flux phi is flowing. Okay, so we have the formula for reluctance S is equal to L by mu M A, or S is equal to L by mu 0 mu R A, where mu R is equal to mu M by mu 0. that is relative permeability. Okay, mu r, and mu 0 is permeability of the free space or air. So, and this, yes, unit of S, unit of reluctance S is equal to meter divided by Henry per meter. Mu r means relative permeability, that is mu m by mu 0. It is a ratio, and it gives a number, and that number has no unit. Okay, so then area unit of area is meter square. So meter square here becomes meter square cancels, then reluctance is equal to H inverse, Henry inverse. This is the unit. Okay, now, okay, that is our reluctance S. Then we have definition for permeance. Permeance denoted by P. It is nothing but the reciprocal of reluctance, like your resistance, like your conductance. Okay, conductance is equal to reciprocal of resistance. So then you can define permeance also. Okay, so there is no nothing difficult in there, in that. Now yes, now I'm introducing a table. Okay, a table in which we are classifying, or we are comparing the two circuits, that is electric circuit, an electric circuit and a magnetic circuit. What are the analogous quantities? Okay, then first of all, quantity is electromotive force, that is electromotive force in EMF in electric circuits, that is analogous to MMF in magnetic circuit. Then current, when coming to the magnetic circuits, we have flux. Then resistance in magnetic circuits, reluctance, and its formula is also here. R is equal to rho L by A, or 1 by sigma into L by A. Here it is 1 by mu 0 mu R L by A. Now conductivity, here permeability. Then conductance, here permeance. Okay, then current density. Current density means we have yes, current density in an electric circuit is defined as J is equal to current I divided by area, that is current passing through unit area. So in a magnetic circuit, we have analogous quantities, that is flux. We have analogous quantity for current, that is flux. Flux phi divided by A, that is flux passing through unit area. That is what we have defined our magnetic flux density B. Okay, so that means we have as current density. When coming to the magnetic circuit, we have flux density, Weber per meter square, or Tesla is the unit. Then electric field intensity, we have magnetic field intensity. Then Ohm's law, we are defining Ohm's law in an electric circuit, that is I is equal to E by R, and in the same manner we can define Ohm's law in a magnetic circuit. That is the beauty of this subject. that is Ohm's law in a magnetic circuit is defined as yes, in an electric circuit it is nothing but I is equal to E by R or equal to V by R. Okay, so right, I'm writing analogous to each parameter in the electric circuit. Then we have flux phi is equal to E means MMF, magnetomotive force here, divided by R resistance. Here we have reluctance S. Okay, this is the Ohm's law. This is Ohm's law. Ohm's law in a magnetic circuit. Okay, so this is very important formula that we will apply to find out the MMF or reluctance or flux through a magnetic circuit, through a given magnetic circuit. Okay, so we will solve a problem. We are going to solve a problem. Okay, so this is the problem. Yes, a coil of 200 turns is wound uniformly over a wooden ring having a mean circumference of 60 centimeter and a uniform cross-sectional area of 500 mm square. If the current through the coil is 4 ampere, calculate first of all the magnetic field strength, that is H, then and the flux density means B, and the total flux. So these are you have to calculate. So okay, I will solve this example, and the next example you have to example 6.3 and 6.2 you should solve as assignment. Okay, and this here we have given that the the examiner given that is given a ring, wooden ring like this, and in that winding are placed. Okay, winding is placed like this, and mean he or she has given the mean circumference. That's equal to mean circumference is equal to given that 60 centimeter. Okay, so this is 60 centimeter, and other details are yes, a coil of 200 turns is wound uniformly. 200, so here n number of turns for this coil is 200 turns, and yes, and it is having a uniform cross-sectional area 500 mm square. 500 mm square means yes, cross-sectional area is this, that is a 500 mm square. Now the examiner has given that the current through the coil is 4 ampere. That is, if current of magnitude 4 ampere is flowing like this, in this manner, it is flowing. Okay, so this is a magnetic circuit. There is no doubt about that. Right, a magnetic circuit. So, and this is like a toroid, but the medium, the core medium is a wooden, a wood. Okay, wooden core medium. So Wooden core medium means, actually the examiner is telling, actually this wooden core medium means, core medium, actually this core medium is equivalent or equal to our air. Why? Because this air is a diamagnetic material, and wooden material, any wooden material is also, or wood is also a diamagnetic material. Okay, so we can conclude that this is equivalent or equal to air. So that means indirectly the examiner is given mu 0 mu r, that is mu m equal to mu 0 mu r, and mu r for air or wood or any diamagnetic material, it is 1. Okay, so mu m will be equal to 1. Sorry, mu m will be equal to 1 into mu 0, that is equal to 4 pi into 10 power minus 7. Okay, so in the place of mu m you have to substitute this value for 4 pi into 10 power minus 7. Okay, okay, now the examiner is asking you to find out the magnetic field strength. Magnetic field strength is what? Your H, and that is equal to Ni by L. So that will be equal to 200 into 4 divided by mean circumference, that is 60 centimeter, that is 0.6 meter, 0.6 meter, that's equal to, yes, 1,333 ampere per meter, 1,333 ampere per meter, or 1,333 ampere turns per meter also right. These two are right. Okay, unit. Now the flux density, right? Flux density is what? Flux density, we have the formula B is equal to mu 0 mu r h, or B is equal to mu m into h. Here B is equal to mu 0 h. So we have B is equal to 4 pi 10 power minus 7 into 1,333. Okay, that much Tesla or Weber per meter square, right? Okay, so the answer is 1675 micro Tesla. Okay, that much small. Now the examiner is asking you to find out the total flux. Total flux means total flux phi will be is equal to, phi is equal to actually B. Actually B, by definition of flux density, B is phi by A. So phi is equal to B into A. So phi is equal to this 1675 1675 micro means into 10 power minus 6. Okay, into area cross sectional area. Here the examiner given 500 mm square. 500 mm square means into 500 into 500 into mm means 10 power minus 3 when you are converting to meter square. So 10 power minus 3 square. So phi will be equal to some, yes, point, this answer 0.8375 microweber. So microweber means it is very small. Okay, very small. So that is our example problem. Okay, now as an assignment I will give you the some other questions, that is two more questions I will give you as assignment. Okay. Then next we have to discuss the composite magnetic circuit. Yes, composite magnetic circuit. And in this topic, composite magnetic circuit means, actually we have discussed this composite magnetic circuit in the first class, but actually you didn't realize that it is a composite magnetic circuit. Simply you have understood it is a magnetic circuit. So recall, you recollect our previous example of a toroid like this, or a, yes, or a magnet like this. Okay, in a C-type magnet. Okay, and we have current I flowing I. Okay, so n number of turns. So what we will have, Ni, that is of magnetomotive force will be generated. So that now we have, yes, we have this C-type material. It is made up of some cast steel, and we have in between we have air. This is air or vacuum. Okay, so the thing is, the when yes, the flux will, here the flux will, definitely flux will flow in this manner. Okay, but the flux will when traveling from cast steel to air. Okay, cast steel to air, or when it is traveling through the cast steel, it will experience an opposition or reluctance S1. Okay, and when it is passing through air, it will experience a different opposition, different amount of opposition, or different magnitude of opposition, that is S2. Okay, like this different magnitude of opposition this flux will experience. So why because S1, for S1 reluctance to have, we have cast steel L1 length, suppose it is having, and L1, then mu cast steel, means mu of the cast steel into A1 we have. So S1 will be L1 divided by mu into A1. That means L1 is different, A1, mu cast steel, all these are different. So S will be a particular value, that is denoted as S1. And this S1 is different from S2. Why? Because S2 is again L by mu A, but the length is different, that is length is much shorter, so this is L2, and area of cross section is also different, A2. Why? Because if you are considering an area of cross section like this, okay, a column of air and its cross sectional area, then it will be, okay, it will be equal. Actually A1 will be equal to A2, A1 will be equal to A2. Okay, but L2 not equal to L1, and also mu is permeability of the medium, mu m is actually mu 0. So this is also different. So two parameters are different, so the ratio and the equation is also different. So S1 S2 two reluctances will be there. Okay, so in this kind of a magnetic circuit is known as composite magnetic circuit. That means two or more different magnetic materials or different magnetic paths are joined together to get the composite magnetic circuit. Okay, so that is our composite magnetic circuit. And in this case, in the case of a composite magnetic circuit, actually this first medium, that is cast steel and air, okay, with respect to the flow of flux, these two material are in series, right, in series. So the net reluctance so the net reluctance S total or S effective will be equal to S1 plus S2. That means whenever yes, it is like your electric circuit. In an electric circuit, current is flowing like this, okay, and it is uh, flowing in two different materials which are connected in series, okay, like this, two different materials. So this conductor may be having a resistance R1 and this conductor may be having a resistance R2. So the net resistance or total resistance or effective resistance will be R total will be equal to R1 plus R2. So similarly, in the same manner, we have in place of I we have phi, okay, and in place of R1 R2 we have S1 S2. So this is true. S effective equal to S1 plus S2. Okay, so for the time being, I think it is enough. Okay. Okay, thank you.